The Sun has unleashed a significant X-class solar flare, accompanied by a substantial coronal mass ejection, CME, hurtling towards Earth. This event represents a notable space weather phenomenon with the potential for widespread impacts ranging from dazzling auroral displays to disruptions in satellite communications and power grids. The core of this analysis focuses on understanding the event itself, the X-class flare and the associated CME. We will delve into the background of solar flares and CMEs, their classification, mechanisms of formation, and historical precedents. We will then explore the projected trajectory and potential impact of the current CME on Earth, considering factors like arrival time, intensity, and geomagnetic storm classification. Finally, we will assess the potential ramifications across various sectors, including communication, navigation, and energy infrastructure, and offer a concluding perspective on the overall significance of this space weather event. Solar flares are sudden releases of energy from the Sun, manifesting as bursts of electromagnetic radiation across the spectrum, from radio waves to X-rays and gamma rays. They occur in active regions around sunspots, which are areas of intense magnetic field concentrations. The energy released in a flare is enormous, equivalent to billions of megatons of TNT. Flares are classified according to their peak brightness in the soft X-ray wavelengths. The classifications are A, B, C, M, and X, with each class being 10 times more powerful than the previous one. An X-class flare is the most powerful category, capable of causing significant disruptions on Earth. CMEs, or coronal mass ejections, are massive expulsions of plasma and magnetic field from the Sun's corona. These eruptions often, but not always, accompany solar flares. CMEs can travel at speeds ranging from a few hundred kilometers per second to over 3,000 kilometers per second. When a CME impacts Earth, it can interact with the Earth's magnetosphere, causing a geomagnetic storm. Historically, large solar flares and CMEs have had significant impacts. The Carrington event of 1859, the largest recorded geomagnetic storm in history, caused telegraph systems worldwide to fail and produced auroras visible as far south as the Caribbean. More recently, a powerful CME in 1989 caused a major power outage in Quebec, Canada. These historical examples underscore the potential for space weather events to disrupt modern technological infrastructure. The current CME is projected to impact Earth within the next 24 hours. The precise timing and intensity of the impact are still subject to refinement as scientists analyze observational data from space-based telescopes and ground-based observatories. The projected geomagnetic storm classification will determine the severity of the potential impacts. A G1, minor, storm might only produce weak power grid fluctuations and have minor impacts on satellite operations. A G5, extreme, storm could cause widespread power grid collapse, satellite damage, and significant disruptions to communication and navigation systems. The primary impact of a CME is the compression of Earth's magnetosphere, leading to geomagnetic disturbances. These disturbances can induce currents in long conductors, such as power lines and pipelines, potentially overloading them and causing blackouts. Satellites are vulnerable to damage from the increased radiation and electrical charging that occur during geomagnetic storms, potentially disrupting communication, navigation, GPS, and weather forecasting services. Radio communications, particularly high-frequency, HF, radio, can be severely disrupted due to ionospheric disturbances caused by the CME. Airline flights over polar routes may be rerouted to avoid increased radiation exposure for passengers and crew. In summary, the X-class solar flare and associated CME represent a potentially significant space weather event. While the exact intensity of the impact remains uncertain, the potential for disruption across various sectors, from power grids to satellite operations, is real. Continued monitoring and forecasting are crucial to mitigate potential risks and implement protective measures. The occurrence underscores the importance of ongoing research into space weather phenomena and the development of robust strategies for safeguarding critical infrastructure against the impacts of solar activity. The expected aurora displays, while visually stunning, are a byproduct of a force that demands our continued attention and respect.